Okay, looking at the single problem, pretty big problem, that I gave you for chapter 15. Before I get started, I made a table over here to summarize the different thermodynamic processes. So these are all for ideal gases. The internal gas law, or ideal, gas law, PV equals nRT equals capital N KT. Remember that N is equal to capital N over capital NA, that is lowercase n is the number of moles, is equal to capital N, the number of molecules, divided by N sub A, which is Avogadro's number. For an ideal gas, and you need to know what the ideal gas is, that equation is going to be true. Also, for an ideal gas, the internal energy is going to be NCVT, N number of moles. CV is the molar specific heat capacity at constant volume, which for any ideal gas, well, I say for any. For a monatomic ideal gas, it's always F over 2R, where F equals the number of degrees of freedom. The issue that makes this not always every time is because for monatomic ideal gas, F is 3, and it's easy. For a diatomic ideal gas, because of quantum mechanics, at really low temperatures, F is 3. At room temperatures, F tends to be around 5 because you have high enough temperature to access another form of energy. And at really high temperatures, F will be 7. So for monatomic ideal gases, F is equal to 3. And everything we're doing here is with helium, which is a monatomic ideal gas. I chose that so we could do this. So now we have the isochoric process, and isochoric is constant volume, which means, according to the ideal gas law, pressure divided by temperature is a constant. The heat for an isochoric process is QV, I put the subscript V just to indicate it's a constant volume, is NCV delta T, where CV is 3/2 R for monatomic ideal gas. The work is equal to 0. That TF is a limit for the integral below. And then the entropy, change in entropy at constant volume is, well, the equation, I did this with calculus so the calculus students could see it, and other people could see there's a reason we come up with these equations. The equation for change in entropy is always delta S is equal to integral of d slash q over t. D slash, because it's not a proper derivative, when we put q is equal to ncv delta t, that's actually a transfer of energy. And so I replaced dq with the same thing that I had up there for q, the ncv dt. That's just calculus changing delta to d. And so when you do that integral, you have the integral dt over t times constants. So you have the constants times natural log of t final over t initial. So we have the equations here for work, change in entropy, heat, and the internal energy is the same for all of them. For isobar, an isobaric process has constant pressure, so volume over temperature is a constant. And in that case, the heat is NCP delta T, where CP is just CV plus R. So for monatomic ideal gas, it goes from 3/2 R for CV to 5/2 R for CP. And for constant pressure, the work is very simple. It's pressure delta V. The equation that's always true is, work is equal to integral of P dV. That's the equation that's always true. So for an isobar, that's just P delta V. Then for the change in entropy for an isobar, we do exactly the same as we did for isochoric, except for the Q now has CP instead of CV. So we have NCP, natural log of T final over T initial. Isotherm means constant temperature, so pressure times volume is constant. And in this case, the heat is equal to the work. Where does that come from? That is simply looking at, I see I erased the volume there, my limit. That's simply coming from the first law of thermodynamics. It says energy can't be created or destroyed. So delta U is equal to Q minus W. For isotherm, from an ideal gas, the internal energy is proportional to temperature. So that means that the internal energy is constant. Maybe I'll add that up here. delta U equals 0, since the change in temperature is 0. And so the heat will just be equal to the work. And we calculate the work by doing that integral of P dV. Well, since P times V is constant, I just said, let's let P times V equal P initial, and initial times V initial, divide both sides by V, and you have P is equal to P initial, V initial over V. That integral then, the P0, V0, is a constant, so you have integral of dV over V, which gives you natural log of V. Using the ideal gas law, I could also write this in actually a more friendly form, I think. Notice I don't have to put T initial or final there because it's a constant temperature. So the second form, the one I wrote in black, is probably the more useful one. And then for isotherm, the change in entropy is just Q over T since the temperature is constant. And finally, for an adiabatic process, I don't have an adiabatic process in this problem here. I probably should have put one in. Adiabat means that the heat is 0. There's no heat. And since entropy is change in heat, well, the heat over temperature, if the heat is 0, there is no entropy change. So it's also called an isentrope, constant entropy. And then this last one, I did not show a proof for it here, but pressure times volume raised to the gamma is equal to constant. What is gamma? Gamma is defined as Cp over Cv. So for a monatomic ideal gas, gamma is equal to 5 halves divided by 3 halves is equal to 5/3. Okay, and so then to calculate the work, it's again integral of P dV, but now I use this pressure times volume to the gamma is equal to constant. And so pressure volume to the gamma is equal to pressure initial volume initial to the gamma. Solve that for pressure by dividing by volume to the gamma. And so pressure is pressure initial volume initial to the gamma over volume to the gamma. And so when I do this integral, I have the constant stuff, pressure initial volume initial to the gamma, times 1 over, oh my goodness. No, I did it right. Thought I had a sign error there. 1 over V raised to the gamma minus 1, and then I put in my limits here, divided by the new power, which is minus gamma plus 1, since it's in the denominator. Anyway, then you just carry through the algebra. I replaced P initial, V initial to the gamma with P final, V final to the gamma for the term that had a V final. And I get a fairly simple equation in the end for the change in entropy, for the work for an adiabatic process. Okay, so let's get to the problem. So reading the whole problem, you start an experiment on 5.0 moles of a monatomic ideal gas at standard temperature and pressure. I guess it was a different problem that was helium. This is just monatomic ideal gas. And it's at standard temperature and pressure. Standard temperature is 0 degrees Celsius. Standard pressure is 1 atmosphere. It is then allowed to expand at constant pressure until it doubles the volume. It then is allowed to further expand at constant temperature. So let me put the expand at constant pressure, and then it expands at constant temperature until it reaches 3 times the initial volume, and then is compressed at constant pressure until it reaches the initial volume, and then is pressurized at constant volume to return to the starting state. Calculate the heat work, change in entropy for each transition and for the entire cycle. If this is used as a heat engine, what is its efficiency? All right, so we've got everything laid out. Now, how to solve it. First, identify the name for each of the processes. So the first one, expand at constant pressure. Pressure is bar, so that's constant iso pressure bar. So it's an isobar. Constant temperature expansion, iso for constant, therm for temperature. Constant pressure contraction, well, that's the same as the first one, an isobar. Then constant volume pressurization, that's the one that's confusing because instead of calling it isovolumetric, we use the term isochore. It's an isochoric process. Now I have draw a PV diagram. PV diagrams really help me in doing these. So I have pressure, volume. I know I start with some volume. I go to double that and I go to triple it. So there I have my volume values, V initial, 2 V initial, and 3. That's not a 3. 3 V initial. And I should spell out the word volume. It's kind of bad to just put V there. So volume, and I'm just putting arbitrary units. I'm not going to write the units because I ran out of space. I'm going to forget it. That thing is just going to stay there for all, not all time. I've got ways around this. There we go. And this axis likewise should be pressure. And I know that I start at 1 atmosphere. So pressure in units of ATMs. And we know it's going to move from there. So now let's mark the points. We know we start with 1 atmosphere and volume of V initial. Don't know the values of, well, the value of V initial right now, but that's, I'm going to call state A. Now we have constant pressure until it doubles the volume. So it's going to go, and there I'll call it state B. Then we have an isotherm to get to state C. There should be some curvature there. I'm going to draw it with more curvature just to make it more clear. And then we have an isobar again coming back to state D. And then we go an isochore up to state A. So there's my PV diagram. I can immediately tell this is going to have a positive energy or a positive work because that is a clockwise cycle. Clockwise cycle tells you there's positive work in it. So now I've drawn it. Now we calculate temperature, volume, and and pressure. Nice work. At each state, along with the work, heat, energy, work, heat, and energy change. Wow, I must have done this late at night. An entropy change between the states. Yes, I see what I did there. I had these as separate things and combined them. It should be a comma, lowercase, comma, because I very much believe in the Oxford comma. An entropy change between states using the ideal gas law and appropriate equations for the transition type. Those appropriate equations are all over to the right in that table I made. So, starting the process, use the blank to calculate volume. Well, that's pretty straightforward. The ideal gas law. The ideal gas law relates PV and then RT. Now, at this point, I have to address what units am I going to use. I was given units of moles. Well, good. That's lowercase n. Pressure in atmospheres. I could, and this would be the wise choice, I could use pressure equals 1 atmosphere equals 101 101,325 pascals. If I do that, all of my units are going to work out just as easy as pi. I recommend you do that. I, in my not so infinite wisdom, chose to say, well, I have atmospheres. Let's use the units of liters, atmospheres, and moles and go from there. And so I did my calculations and I made this table here to put in the numbers in units of atmospheres, kelvins, liters. Well, like I said, that was a foolish decision. But I'm sticking with it because, hey, it gives us some practice. So using PV equals nRT, that's going to then tell me that V is equal to nRT over P. That's 5.00 moles times R. Well, now we have an issue. What R do we use? There's multiple R's. And this is the true reason why I chose to use these units. The R value in units of kelvins, moles, and, well, kelvins, moles, atmospheres, and liters is 0.08206. And I don't have room to put in the units there. I don't even have room to put the temperature. Temperature needs to be in kelvins, so that's going to be 273.15 kelvins. And then divide by the pressure of 1 atmosphere. And doing that calculation, I get that the initial volume is 112.07 liters, which is equal to, if you want to convert it, 0.11207 meters cubed. Right? If you're going to use the normal units, you'd have 0.11207 meters cubed. Use the internal energy equation for monatomic ideal gas to calculate the internal energy. U is equal to 3 halves nRT is equal to 3 halves N. For this one, I want to get my answer in joules, and I have my temperature in kelvins, so I am simply going to use the standard of 8.31446, and that would be joules per mole kelvins, and then times the temperature of 273.15 kelvins. And that gives me an internal energy of 17,033 joules. So there I have the information for state A. So let me go ahead and put that in my table right now. 112.07 liters and 17,033 joules. Now we have the transition from A to B. And so the first thing I'm going to do is, I know the pressure and volume. I know the volume because I know it's doubled. So use, again, the ideal gas law to calculate the temperature. So I'm going to have, now remember, PV equals nRT. If it is an in this case, an isobaric process, the pressure is constant, and we have V over T is V1, or VA TA is equal to VB TB. That's supposed to be an A, and I can't write an A. So it's actually real quick to calculate the new temperature. Temperature B is equal to temperature A times VB over VA. Well, VB over VA was 2, right, because it doubled in volume. So that means temperature A is equal to, or temperature B is 2 temperature A. And so I will immediately put that number in my table. The temperature doubles to 546.30, and the volume also doubled, so it's going to be 224.14. And now I can calculate the internal energy. I'm not going to spend the time. The internal energy will be calculated with exactly the same equation. So because we doubled the temperature, we're going to double the internal energy, 34066. Now, that's calculated the internal energy. Use the appropriate equation to calculate the heat added to the system going from B to C. Well, because this is going from B to C, whoops, wrong one. Use the appropriate way to calculate the work going from A to B. So I did the work first here. Why? Well, because if it's an isobaric process, the work is a very accessible calculation. Work is equal to P delta V is equal to 1 atmosphere, or 101325 gals, the change in volume, which is, and I'm going to put it in meters cubed. So the change in volume is final minus initial, 0.22414 minus 0.11207. And that gives me a work of 11,355 joules. Another way that you could have done the work, I'll change color for this, would have been to use 1 atmosphere times my change in liters volume, 224.14 liters minus 112.07 liters. And that's going to give you a number that's, that's in units of atmospheres times liters. And I have to change my spreadsheet because I already applied my conversion factor. So that gives you 112. Need more significant digits than that. 112.07. And the units for that are going to be atmospheres times liters. Well, atmosphere times liter is not a standard unit of energy. So we have to take that and we have to multiply it by our conversion factor, which is the 101335 pascals per atmosphere, 325, excuse me. And 1 meter cubed per 1,000 liters. If you put those two together, that gives you 101.325 as the conversion factor. And so I could have done my calculation of those units and then used the 101.325 joules per atmosphere times liter as a conversion. At any rate, what I found is it's 11,355 joules. So I'm going to put that in before I forget. $11,355. Hopefully that's what I ever put. 11,355 joules of energy for the work. Continuing on, using the Planck law of thermodynamics to calculate the heat added. The Planck law. Well, this is an isobaric process. We have the heat is going. The way that I chose to do this here, I was using the first law, and you have delta U is equal to Q minus W. Therefore, Q is equal to delta U plus W. So delta U, because the temperature, this is the isobar. We calculate the work. We can calculate the internal energy. We've already done that. So we know the change in internal energy. We could use that. There's a second way to do it, right? More than one way to skin the cat, as we say. And that is to calculate Q is equal to NCP delta T. And if you do it either way, you're going to get the same answer. So I'm just going to do it this way. Equals 5.00 moles times CP. CP is going to be 5 halves of R. And I'm going to use the standard units for R, 8.31446. that's 6 joules per mole Kelvin. And then times the change in temperature. The change in temperature was 273.15 kelvins. And that gives us a heat of 28,389. So putting in these values, we have the heat is 28,389 joules. And now I didn't put anywhere for the change in internal energy, so I'm going to write it here. The change in internal energy, how I actually instructed you to calculate, is 17,033 joules. Now I have to calculate the change in entropy. I will go up there. The change in entropy for an isobaric process is delta S is equal to NC pressure, natural log, temperature final over temperature initial. So that's 5.00 moles times 5 halves times 8.3144, 6 joules per mole times Kelvin, times the natural log of temperature final over temperature initial. I'm just going to put 2 over 1 there. It's quicker than writing out the numbers. And so doing that calculation, I have a change in entropy of 72.04 joules per Kelvin. So that fills out the second transition. Going from A to B. Well, that's the first transition. Fills out the second state. Now we're going to go from B to C. So we know the volume and temperature because we know that it was now constant temperature and the volume has gone to 3 times initial volume. So again, use the ideal gas law to calculate the pressure. So once again, if PV equals nRT, if the temperature is constant, that means PV is constant. So pressure C, volume C is equal to pressure B, volume B. Divide both sides by volume C, and we get pressure C is equal to pressure B times volume B over volume C. That's equal to pressure B times 2 volume A over 3 volume A. So it's just 2/3 pressure B, or 2/3 of an atmosphere. So 0.66 repeating atmospheres. Or if you want it in units of pascals, that's equal to 67,550 pascals. So we've got the pressure. Use internal energy equation to calculate the internal energy. Well, the temperature stayed the same, so I don't need to do that calculation. I know it's the same internal energy as before. Using internal energy numbers, calculate the change in internal energy. So change in internal energy is 0. Use the appropriate equation to calculate the heat added to the system going from B to C. Well, this here is an isothermal process. For the isothermal process, you can't use Q equals, something times change in temperature. That doesn't work out. What you actually have to use is Q is equal to the work. That comes from the second law, or the first law, delta U is equal to Q minus W. Therefore, Q equals the work, and work is equal to, and I have the equation up here in this is isotherm. Work is equal to nRT, natural log of V final over V initial. Is equal to 5.00 moles times 8.31446 joules per mole Kelvin times 546.30 kelvins times the natural log of, and from the work we just did, V final over V initial is 3/2. And so when you do that calculation, you find that both the heat and the work are 9,208 joules. Then using the which law, calculate the heat. Oh yeah, see this one here should have been calculate the work, and then use the first law. I made some mistakes here. I'm going to go ahead and make this sheet and correct the mistakes. So the one you see, if you check it after this, will be correct. Calculate the heat added. Okay, so we've done that. Use the appropriate equation, calculate the change in entropy. Well, this is the easy one. Delta S is equal to Q over T. So that's going to be the number we just calculated, which was 9208 joules divided by the temperature, 546.30 kelvins. And that gives us 16.86 joules per Kelvin. So let's fill that one in. So this one here, we've calculated 0.66. I'm just going to put 667 here. And then the temperature is again 546.30. The volume is 336.21 liters. And the internal energy stays the same because the temperature stayed the same. The heat was 9208. The work was 9208. The change in entropy was 16.86. And the change in internal energy was 0. All right, let's go from C to D. So now it's gone back to our initial volume. So we know the volume. It stayed at constant pressure, so we know the pressure. So now we're going to again use the ideal gas law. Right? We did the same thing over and over to calculate the temperature. So I'll just calculate the temperature. Once again, constant pressure, just like before. Volume over temperature is constant. For this transition, therefore temperature D is equal to temperature C times volume D over volume C. Well, volume D is 1/3 of volume C. So it's 1/3 temperature C, which is 182.10 kelvins. Now use the internal energy to calculate or use the equation U is equal to 3/2 nRT. That's going to be, let's do the things faster, smarter. That's going to be equal to 1/3 of what we had for the internal energy last time, because the temperature is 1/3. 1/3 UC. And so if we just take 1/3 of the internal energy we calculated for the last one, we're going to have 11,355 joules. From the internal energy numbers, calculate the change in internal energy. Okay, so we went from 34066 down to 11,355. So you always take the final first. And that's going to be 22, that's a nice 2, minus 22,711 joules. So now we had a drop in internal energy. Use the appropriate work equation to calculate the work done. Okay, so this here was constant pressure, so work is equal to P delta V is equal to my pressure of 0.666 repeating atmospheres times my change in volume, which was final 112.07 liters minus initial 336.21 liters. And then I'm going to need to use my conversion factor. And that gives me a work of, notice it's going to be negative because the final volume was a smaller value than the initial. And so that gives me a work of minus 15,141. And then law of thermodynamics. To calculate the heat added, that is Q is equal to delta U plus work, just like we did before. So I can add those two, or I could have used, Q is equal to NCP delta T. In this case, I'm just going to add those two together. So minus 22711 joules plus a negative 15,141 joules equals minus 37852. That's not added, right? That's a negative value, so that means that that's the heat exhausted. Now calculate the change in entropy. Delta S is equal to N. We just did this. NCP, natural log temperature final over temperature initial. And so that's going to be 5.00 moles times 5 halves times 8.31446 joules per mole times Kelvin times the natural log of, and from our work above, temperature final over temperature initial is 1/3. Well, natural log of 1/3 is minus natural log of 3, so we know it's going to be a negative value. And it turns out this is minus 114.18. Can't read that. Joules per Kelvin. So now I'm going to fill in all of those numbers. And so I have 0.667 pressure, atmosphere's pressure, temperature 182, 0.10 kelvins. The volume at this point is 112.07 liters, back to the initial volume. And the internal energy is 11,355 joules. And then for the transitions, for the heat, we calculated negative 37,852 joules. And the work was minus 15,141 joules. The change in entropy, minus 114.18 joules per Kelvin. And the change in internal energy, just to get everything complete, was minus 22711 joules. Final thing then, going from D back to A. I already know the state for A and the state for D. I don't have to do any of those calculations. I just need to do the change in internal energy, the work, and the heat. So let's start with the easy. Change in internal energy, I can do that right here. I'm going from D to A, so the internal energy is going up. It's going to be 17,033 minus 11,355. If you do that calculation, you see that you get 5678 for the change in internal energy. So that's our change in internal energy for this cycle. Now we need to calculate the work and the heat. So calculate the change in internal energy, we just did that. Use the appropriate work equation to calculate the work. Work is equal to P delta V equals 0 for an isocore, so that's real trivial. Then use the first law, thermodynamics, to calculate the heat. Since W is 0, Q is equal to delta U. So that was real easy. I have 5678. 5678. Oh, wait, that heat work was 0. And then the change in entropy. Well, for the change in entropy, this one here is isochoric. For the isochoric, we had the change in entropy was delta S is equal to NCV, natural log of T final over T initial. So this is going to be 5.00 moles times 1.5. Well, I'll put the 3 halves to make clear where that's coming from. That's 5 instead of 3. Times 8.3144 joules per mole Kelvin. And then times natural log. Temperature final is 273.15 kelvins. Temperature initial was 182.10 kelvins. And so that gives us a change in entropy of 25.28 joules per Kelvin. So if we go through the totals, for the total heat, we find it's 5423. That is, there was 5,423 more joules added than were exhausted. Where did that go? It went into work. The total change in entropy is 0. It has to be 0 because we ended and started in the same state. Entropy is a value that you have in the state. It's not a variable of state. It's a value you have. Anytime you're in the state, you have that same entropy, so it had to be 0. Now, I put those totals in. We now have to use the definition of efficiency to calculate the efficiency of this heat engine. Note that heat may have been added in multiple steps of the cycle. Use the sum of the heat added to calculate efficiency. So heat added is equal to all of the positives. That's the 11,355 plus 9,208. If you add those together, I looked at the work column, excuse me. The heat, 28,389 plus 9,208 plus 5,678 or 74. No, that's an 8. And it gives you the total heat that you added is 43,275 joules. And so efficiency is equal to the workout divided by the heat added. We called it QH before because we were doing a fairly idealized system. So the total work is 5,423 joules divided by that heat added 43,275 joules. And that gives you an amazing 0.125 for the efficiency. Okay, there we've come to the end of the problem. That was a lot of thermodynamics calculations. There's only one problem, but we went through everything except for adiabatic process. Hope this helps you get ready for the test.